This year there are three people from France: Nicolas Boulet, Cédric Bay, and myself, Yann Guidon. We participate and we contribute to this project for several years, and we will try to make to present useful things for you to hack in the future. There are some points that we will present and discuss quite fast because we don't have much time. I will start and make some I will give some important points for the people who don't know this project. I will present a few simple code snippets to show how to use this architecture to its best. Um, and it's not written in the plan, but I will also present, I'll make a small presentation of the built-in self-test architecture. Then Nicolas Boulet will present how the techniques that are used in general to design and build and make and test microprocessors or electronic circuits in general. And in the end, Cédric Bay will present the outcome of some discussions about calling conventions with FCPU. So let's start with some ideas about FCPU. First, the goal was to make an alternative microprocessor that would allow us to not use Intel or to be free. It's about freedom because hackers were fed up of reading Intel's documentation and not having the right. They did not feel comfortable with signing NDA, etc. So they started imagining something, and years later it became more and more reality, and the utopia became physical, and sometimes it scares people when utopia becomes reality, but it's the truth. But as Richard Stallman says, it's all about freedom, and sometimes I hear free CPU when Ren speaking about freedom CPU. Well, it's very annoying that I don't have a beard yet, so it's not a problem. And yes. Uh, the answer is there is no specific target. And the other questions will be answered in the end of the presentation. We have only 1 hour to fit all that stuff, and it's the fourth year that we are here for the fourth year. So we want to show people that it is not dead, even though the website is not updated because we are electronicians, not webmasters. Ah, so I will give a few ideas about the architecture that has been chosen and developed. So we did, for many reasons, it is best not to use existing architectures like Leon did with Spark, and we wanted high efficiency and a lot of operations per second. So we targeted the architecture toward uh, it is designed a bit like an alpha or MIPS microprocessor that is simple and fast and easy to program, so it can reach and stand peak performance. It uses several ideas from the RISC microprocessors, such as fixed side 32-bit instructions, cache memory, and there are 64 registers which have at least 64 bits. There is a load store. There are load store only access to memory. There is no stack. It must be handled by software. And register 0 is hardwired to 0, so it is a dev null, something like that. and it has some jump call return instructions and everything is designed to be orthogonal. And there is some a specific addition to the usual microprocessors. The goal is to have as much raw power as possible with as few efforts in hardware design or programming. So we decide that register by the model specifies that there are 64 bits per register, and it can be more in the future depending on the target or on the goal of the implementer. So you can implement FCPU with 64-bit for small applications, but if you need video processing or high-speed processing of large data sets in scientific or any or graphics computation, you will turn one button that will enlarge the registers, compile everything, and make, if it is physically possible, you will have larger registers and more, at the same speed, you will have more operations per second without using superscalar techniques which use more logic and are more complex to deal with. And so there is often a misconception about the term register. Sometimes people hear about 128-bit register and they say there's no use because there's no use in such large integers. And there is one integer can fit in one register, but reverse cannot be true. Uh, mm. So there are mainly three data types, and scalar data, which can be integer or floating point or whatever. It is simply aligned on the least significant bit, and mhm. And there are pointers that are a bit like scalar data, but because of implementation reasons, we don't know in advance how many bits will be checked, will be useful for checking in TLB or whatever. So it must be more lax. And SIMD data, which use all the width of the register, and depending on the size of the register, you can fit more data in it. The instructions are 32-bit wide, and of course, they have also the same field at the same place to ease decoding, and it has 8 bits of opcode, and since there are 64 registers, it uses 6 bits for each register, and we can't fit much register operands because they are so large, but sometimes we use some registers for reading and writing, and some extensions like that. Mm. The currently developed core is called FC0 for FCPU Core 0. It is statically scheduled uh, microprocessor, which means there is no it is predictable like MIPS or early alpha processors, so it's easier to code for, unlike the latest microprocessors with out of order decoding. It can issue one instruction per cycle. As I have said before, it is enough for computational codes, because if you want more power, you just enlarge the registers. It is as simple as changing one line in a configuration file, and that's all. However, some units have more latency than others, so there has to be a mechanism to ensure that there is no synchronization problem. So it uses a scoreboard to ensure that when a unit completes before another, there is no problem. And finally, to ensure that the speed is as fast as possible, all the pipeline stages have very small depth, it is around to, to have a balanced pipeline with with same size for each stage, and not end up with one pipeline stage which is longer than others and speeds down the whole processor. Currently, there are almost a dozen of active contributors. Um, a few people are writing the VHDL source code, which is the core of the project. Some people are also trying to translate it into C to simulate it without VHDL tools. Cedric Bay is responsible for maintaining the manual. There are some efforts for porting GCC. There are several assemblers. Some work much better than others, so just pick yours and be happy. There are some there are some discussions about using L4 microkernel as used in HERD to support multi-processor computers. And finally, of course, there are some ideas about using Linux, but you have to understand that the goal of the project is to design a processor, not to port everything, because we have to limit our target, otherwise we will never reach it. So I'll start with a small code. Yesterday I was in this room and I heard the presentation about IE64 and the comparison with Opteron, and there was a small code snippet which had to compare a few characters and jump or return, and it gave me a good idea for showing how FCPU is used. But before that, one has to know a few facts about FCPU. Mhm. One of the tricks that is used and developed in FCPU is some specific execution units, and the ROP2, the logic unit, is very typical because it is how one ID is expanded and can give interesting results in some cases. Uh, Here I show the schematic, the logical schematic of one pipeline stage. Um, one pipeline stage goes from here to here. So we can count in the critical data path that there are 4 gates, including 2 complex gates. So it corresponds to the typical pipeline depth. So it shows that it is simple, but with that we can do powerful things. ROP2 does logical operations like AND, OR, and then XOR, or AND, etc. And it can combine the results into bytes, which can give new masks. And it can be used very well if you have such code where you have to compare one byte with many other bytes. And what you can do is simply, well, it's not obvious, but the simply XOR all the characters that we want to compare with the copy of the input data. The copy is performed by SIMD duplicate, SDUP. So simply it puts a copy of the byte into all the bytes of the target register. Then we load a constant containing all the comparisons we want to make, and in the end we make a comparison, a XOR, with result which is negated, and all the byte results are added together. And if there is one match, then the end result will not be 0, and we can decide whether to jump or not based upon this computation. Then there is another use for this strange unit, which is very interesting in cryptographic systems, or even for bit reversing, or any use you can imagine. For example, imagine you want to put bit 0 to bit 3, etc., etc., etc. First, you make a first mask which contains, for each byte n, the nth bit is set. So for when the byte is duplicated all over the register, only one byte is selected, and then it is added together with another mask which is built from the table above, and it means that one can swap and shuffle bits in one byte with 9 instructions, which is quite efficient considering other processors. So now you understand why such a small unit can be so interesting. Now I will end this small presentation by presenting the power-up technique, which can give other side results and side effects which can interest a lot of people. Well, here is a very simplified view of the microprocessor, which contains a register set and a crossbar, well, more or less a crossbar, and all the units that are tied on this internal bus. And the problem is that one has to test all the dies before they are packaged, and this is often very costly. There is another cost in the test. Often tests are integrated in the buffer between pipeline stages, and with the very small pipeline stages, it is not possible to add another functionality into the pipeline stages. So the solution that is used now is to simply add a signal generator that will give the right signal to all the units. So they circle data all around. For example, data comes from the register set, goes to ROP2, then power-up sequence is finished. We compare this signature to the good signature, and if it doesn't match, then the die is and the idea is simply to integrate all those two parts into the normal data path and include instructions for using this, because the first part is called Huffman distance, distance, Hamming distance, sorry. And the second is often used for generating pseudo-random numbers. So if the hardware is here, it's not worth throwing it away. So it is integrated in the microprocessor model. Okay. So here I have presented a few tricks that can be useful for many people, and I hope it will enhance further and further. Now, Nico.
So hello. I will present you how we design, how hardware is designed, because for a lot of software people it's black magic. So here's the beginning. It's a representation of a transistor. Rapidly, there is two conductor here and here, and when you apply here tension or intensity here, you could create a canal between these two parts. And that's only that effect that is used in numerical circuits. Okay. This is one of the latest Intel transistors, so you could imagine that is far from the model that we shown. It's important that is far because there is a lot of problem of tools, because when you want to simulate timing or something like, it's very, very hard problem. So you could see later why. So this is a wafer. Ouais. It's not so good, okay. So it's a piece of silicium that is now 20 centimeters in diameter, and you can find many chips on it. We call that die. And if the die is bigger, you can put less die on the same wafer. Because the number of faults are the same, you can imagine if the die is bigger, you have more faulty die. So it costs a lot more. Imagine that there is only one big die in this wafer. There are almost no chance that the chips will work. That's the problem of the cost. So this is a chips. So you could see that it's so for making hardware, there is FPGA, so it's you don't have to build. It's easier. You need less tools. Custom and full custom ASIC is much more expensive to do, because there is a lot of verification that it didn't need in FPGA, and if your code didn't work in FPGA, you have just to reprogram it. It's not a big deal. But ASIC, it costs a lot to rebuild your thing. The difference between semi-custom and full custom ASIC, well, it depends on the company, but imagine that, for example, you have some semi-custom logic where all the transistors are made. There is some wire. a chip there is array of transistors on 4, 5, 7 layers of metals. And in semi-custom logics, the two last layer of metals are not made, and just made for your application. So it's far less expensive. But it's not optimized in speed at all. So nowadays, to develop hardware, what we put in mainboard are now put in the same chip. This is what is called the system on chip, or for little system it was called microcontroller. But nowadays, for GSM phone, Texas Instruments make a chip with ARM9, ARM7 plus a DSP for doing all the GSM on later UMTS stuff. So you can put everything you want in the 100 millions transistor. The difficult part, it's really hard to design. So SCPU is the core. That means that it's a kind of component on a board. So this is a logical component that you could put in VHDL with other parts. That's important because, like you could see, for a lot of people for GPL, all the VHDL stuff put together must be open. So all proprietary development must be open. I don't think that many company will want to do that. So it's a little bit like Linux forbid to run proprietary software on it. I think it's a little bit too hard, but few people think it could be a great thing. And having the code of the flip chip didn't give you the way to break the system. So LGPL could be also used for the core. So it's like Leon. So it just protects the core, and FCPU could be used very easily, like Leon does, but there is absolutely no protection against TCPA. On the last part could be a GPL plus a proprietary interface where it's allowed to link VHDL. It's a little bit like Linux kernel. So we could have an interface for the sub design that is open. On the other side, there is a SDRAM bus that is supposed to get out of the chip. So maybe it could be an interesting point against TCP. But license is soon discussed on the mailing list, and position are really strong. So to design the hardware, we are going to write HDL code. So we use language called VHDL, or for American part, but our project in VHDL, Verilog. So this is some strange language that all assessments are made in parallel, and there is some structure to do in serial that represents how hardware work. So I'll show you. I'll try to show you what is supposed to be a simulator. So You have your code, you can simulate it and see all your waveform, how it could work, and you could put some kind of printf in your test unit to see how it works. Then you need a synthesizer to have a netlist. So it takes your code, and it could synthesize a part of VHDL subset. So the results look like that. So it's interconnection of gates, or different kind of gates. Then there is place and route tools. So the idea is to take the netlist and to make a plan of the chip. Here it's an example of floor planning for FPGA. So now FPGA is very complex, so it looks like that. But for chips design, for ASIC designs, it looks the same. Nowadays they mixed what synthesis give is timing results with simulation, with RTL code simulation. RTL stands for register transfer level. It is what is called the VHDL that could be synthesized. And synthesis gives you timing results, so you could imagine the speed of your of your system. Place and route give you even more information about speed because it takes into account wires and something like, but it's not really precise, and things get bigger and slower. So simulator, CPU. So the simulator we could use is NCSim because Cadence gives you some license to play with. Model Sim could be has been used because I could access it in my school. Simili is a freeware. Simili was a freeware that you could find on the internet. This is what we are using currently. It's quite slow, but it's the only tools that could find on the internet that work. Free tools available. GHDL is current work in alpha version that is became GCC in the software world in 1 or 2 years. So for synthesizer, there is a design compiler is 80% of the market. For doing ASIC, it's very, very expensive. Simplicity is the king of the FPGA market, and there is absolutely no free software. You can find something called Alliance from a French university, but it's quite old, unmaintained, and very limited feature, and didn't take into account the new submicronics technology. So place and route tools is mostly Cadence tools, and these kind of tools are going to merge with synthesis because nowadays the signals take a longer time in wires than in gates. So place and route became very, very tricky and important for more density. So now we will have some tools that say VHDL to GDS2 file. GDS2 is the plan of the chip, and there is no free software. So the three tools see before are what is needed, but there is some other tools that are used every day with design. There is no open source software. There is something called static timing analysis that takes the circuits from the end to the input and verifies that some tools called equivalence checker to verify code, netlist, and so on, to avoid get level simulation. At TPG, it's another kind of tools to generate input vector for test in industry. It could be very expensive too, but we must have this kind of pattern to verify that the chip works. List generator is some tools that generate VHDL to enable to verify some complex stuff as memory, to verify that there is no problem in fabrication. Formal proofing could be the next step to help finding bugs. So to conclude, there is a real miss in software tools to make open hardware. So if some people want to help open hardware or free hardware movement, we need much more free tools. So I give the speak to Cedric.
So okay, I will present the call convention about for the CPU, because during the year we have a lot of discussion about this subject, and in fact decisions that are made about this subject have a really big impact on the speed of your software. So what we need for what are the current call capacity of the CPU? We have no special register. That means that you don't have a stack pointer, you don't have a specific address pointer, and you have 63 general register. And we have no real call instruction, but a jump that saves the current address. And we don't have any stack in hardware. That means that we must define a register to say that the stack pointer is here, and how to use it. So what we need to do a call, we need a stack pointer, we need a return address, we need a return value, and we need parameters. So as you can see, nothing is in the specify in hardware, or you can use every register for any of this possibility. So the first the sample I will use to explain the cost of call convention is the easy annoy function. So the idea of this function is that you are a recursive function. You have tail recursive call. That means that in certain case you can you don't need to update the stack pointer to the last called function, and you don't need to come back in your as this position, but you will see that later. So the first call convention, that was the one we use since the beginning of the project. Of course, the register 0 was set to 0. That's normal. But for the user, we say that there was preserved across call for most of them, and we have one that you specify for return address and another for stack pointer. That was very easy to explain, but we have a lot of cost with this call convention. So, for example, before using a register, we need to store it always in memory. That means that you don't have the possibility to do a small function without memory transfer. That's really important, and you don't have the possibility to load to have parameters without doing memory transfer. It's a big cost, in fact. So the prologue will, as the start of the function, will be for an example like annoy. a series of store with the register and in the stack. That's as you can see, we have a lot of saved register, and of course we need to load after that at the end. We need to load parameters after that. So it was not really efficient call convention, but and of course at the end you need to reload all the register you use. So see, it's not you need a lot of memory operation, and you can't implement a tail recursive call with that because you always need to modify a register to do your manipulation before doing a tail your recursive call. So it's a bit tricky. So the second come at the beginning of this year, and it was less more like the MIPS call convention. So we have some parameters register. That means that these registers are not preserved across call, but it's where we put the first parameter of the call. If we don't have enough register for parameters, we put them on stack. And but with this, most of the call can be done with only register because 14 parameters is a lot. We specify a path for temporary register. That means these registers are always you must think that they are discarded when you call another function, but you can use it at the beginning of the function without any memory operation. That's really useful for terminal function and it reduces global memory pressure. We have, of course, always saved temporary. That's always needed to the code. Okay. So the prog is a little bit smaller because we have some register for temporary register, and we don't need to save them. And for the load, it's the same thing. So we have really we have divided by 2 the number of load and store in the code finally, with only changing the call convention. So the cost is very important. The cost of a good call convention is really important. So for example, with the V6 convention, we can do something like that. When we have a recursive call, we can put at the beginning of the code a loop start, so that instead of doing a normal call, we will jump to an address just after the beginning of the function, where all the cached data and all the things like memory generic operation are still done. It will reduce it will enhance cache. You will use more as cache, and it will your code is quicker with that. So, but another idea comes that we have the problem is that we don't know if the register, saved register, need to be saved or not. Because in some cases, we can imagine that we save a register where no value, no important value, no useful value are in it. So the idea was to give a mask to the function that we call, that say, I use this saved temporary register, this one and this one, so that when I do my own saving register, I'll not always need to save register. That's reduce memory. That's one to reduce memory pressure. But so we introduced a new idea, that's temporary, and this one was mask store. That means that you give a mask of that say which register to save. But as you can see, you have only small prologue to save everything, and let's continue. And a very short epilogue. But in fact, that hides a lot of cost because these functions are asynchronous, complex. When you must know when the fault happened. That means that you must count before doing your transfer which register you need to save, and it's really a big problem. And in fact, to have the best performance, you must be sure that you have no collision between each function. That means that if you have a register allocator that say just iterate and only does give register in the same order every time you run it, you will never have again a performance impact with this solution because you always have you always need to do your store. So and in fact, it's possible to implement it with a conditional store and without using a complex instruction and without any cost for the hardware. But finally, the current accepted for call convention is without mask register because we find another idea that's really better. And this one will do the register allocation pass at the linking time. That means we have an instruction set that is really clean. You have always the register at the same position. You have when you read the OP code, you always need where are the register and which you need to update. And with that, you have the possibility at the linking time to know the call graph, and to by adding some information to the health, you can know which register are used and how many registers are used per function, and you can reduce at the maximum collision into your register bank. And currently, it's a solution. The solution we have selected for the project because we have still we don't need to implement it yet, but because we have a backward compatibility with the normal thing on other no. Register allocator that are written actually don't work with max register and the complex thing. And with linking solution, we have the same. We can use the same tools without any problem with them, and we have always the best result. We only need to write the linking tools. So just in time. So if you have question, I think that you. Question?
Hello. When we look back to your code examples, you had SP as a symbol. Is it an alias in the assembler? Because you told us you had no real stack pointer. It's just a convention.
It's only to easier for you to see where we have the stack pointer. But in fact, some of your assembler have defined capability and those things so that you can put a SP. But it's really, you are right. It's not really a special register.
It's
That's
just an
the method
alias
to register 63 or 62.
Okay.
So it's like that.
I still do not quite understand why you designed your own architecture. I mean, why didn't you just take the Spark architecture, which is non-proprietary, and write an open VHDL model for it? And then all the software problems are solved because, of course, the software is already there.
Yes, but the main reason is not fun. And the second one is still exists. It's called Leon. It's a Spark V7-like. It runs between 100 and 200 megahertz for .18 micron technology. So you can find it. You search for Gessler.com website and you will find it. One of the things is to test a lot of new things like making a real SIMD processor. Try to find much higher trick by managing cache or things like that. Nowadays, FCPU has a little bit less complex than it could be because it's much simpler to code. But re-implement Spark that is 20 years old was not the goal of the project. Other question? Other question?
In fact, there are many reasons to do it. It started like fun, and then we realized by doing it that there were more things at stake, like independence from patents, copyright and microcode problems. So by starting something from scratch, we avoid many things. And if you look closely at the core, at the FC0, you will find techniques that were used 40 years ago in mainframes. But if we use these techniques, because they are so old, we don't have any patent problem, and we use very well-known techniques, and we can find new ways to use them, and we can have more interesting solutions, and we can propose different solutions.
Other question?
Well, there is often one question that is asked: when will it be ready? Well, if we knew. Well, the problem is not time. The problem is doing it. It's the most important thing. Then when it will be done, we know that by speaking with industrial people, it's only if the source and if all the framework for VHDL compatibility is done, it will be accepted very easily. So we have to care about designing it, making it, and testing it, and the rest will certainly come itself.
I have a final question to the audience. Could you please give me a show of hands? Who of you would be interested to have a microprocessor core that can be cheaply synthesized into FPGAs to do embedded control? So who would be interested to get such a core? 1, 2, 3. So this is a lot. I'm about to release such a microprocessor under the name of Microcore at the beginning of next year, and the licensing policy is even more liberal than the GPL license. And after your show of hand, I will give a presentation of this processor core next year. Thank
you. The goal was not only embedded. That's all. It is very broader.
There is still the learn that could came in very. If someone knows the Xilinx XV 300, you could put the Leon. It use 5,000 CLB, so it's very few.
I have a question too. Can you give an outlook of the memory architecture and what improvements you are planning to make?
Well, memory architecture will use a Harvard design, usual one, but it could be have many tricks like multi-load and store that could manage a complete cache line in one cycle to load 4 registers at the same time. Something like that could be implemented, but there is some restriction because all memory access must be aligned, so we have to discuss about that. Besides that, it could be have really interesting things when you use a multi-core design, and it's still in discussion, but there is a lot of work to do before presenting anything. And the goal of the project was really to do the FCPU core before It was the step behind that, to do multi-core design, and that could work with many, with many cores. Other question? Finished? Okay, thank you.
Guten Morgen.